Okay, it's now going to get more complicated. You probably didn't think it would be an Extension 1 topic and stay that straightforward. So the way it becomes more complicated is in the statement that you're trying to prove true. You will see that there are basically 3 types of statements. You can categorize them into 3 types. I'm going to do lots of scrolling and I apologize, but I hope this works. The first type is like the one I just did, and it's a statement that contains the sum of terms. So there it is again. That is an example. I want to scroll down and show you more of those. That's the same one. That's the one I just did. Example 2. Here's another example. Prove by mathematical induction that for all integers greater than 1, here is a sum of terms equaling another statement. Another expression really. So that would be another one, slightly different but similar in that it's presenting you with an expression that is the sum of terms. I think 3 is the same. Yes, we're adding together terms, and that sum could be replaced with this expression. Now I think, no, one from a past HSC where they were lucky. This is the nicest type to get, and you'll find that after having done a few, they're not too bad. You follow the process and you've got it. Type 2 is, as it says here, a proof of a divisibility or a multiple. What does that mean? Well, let's just read some examples. Prove by mathematical induction that 3 to the n minus 1, 3 to the 4n minus 1 is divisible by 80. So that's what we mean when we say that their statement includes divisibility. So that's example 1. Let's see if I've got another one. Use mathematical induction to prove 5 to the power n plus 3 is divisible by 4. I've got another one. Prove by mathematical induction that x to the n minus 1 is divisible by x minus 1. So you can see it's a very different statement. There's no sum of terms here. It's just straight out that is divisible by something else. Got one from the HSC, 2013. Use mathematical induction to prove that 2 to the 3n minus 3 to the n, this statement, is divisible by 5. So again, and it's nice 3 marks. You'll see that they're very generous in their marking for mathematical induction. Here's another one. Prove by mathematical induction that is divisible by 12. Okay. And then we go on to type 3. So type 1, an expression with the sum of terms. Type 2, what we're trying to prove has something about being divisible by a term. And type 3 is the most difficult one, the difficult type to get. It's proving an inequality. So that should be pretty obvious. There's going to be a less than or a greater than in the actual statement. I know that they put a greater than for your values of n, but also you'll see another inequality in the statement. Prove by mathematical induction that for all integers n greater than 5, that n squared is less than 2n. Remember, I'm just showing you examples, so we've got the idea. Use the principle of mathematical induction to show that 4 to the n minus 1 minus 7n is greater than 0. So here's the inequality. So it's not a sum we're proving, it's not a divisible by a term type, it's an inequality type. And that looks like the end. Okay, back to the beginning. We can see now, and we understand what this means. There are 3 question types, and I'm going to call them type 1, which is where you've got the proof of the sum of some terms. 2 is proof of a division, where this statement is divisible by 6. Proof of an inequality, that 2 to the n is greater than n. We need some more information about steps, really step 3, because step 4 is just, we can make a comment about step 4. Step 3 requires some good mathematical knowledge and working. You'll be substituting, you'll be simplifying, you'll be working with indices, you'll be factorising. Your algebra has to be something that is not going to hold you back from getting through step 3. So the nature of the statement will be a guide as to what aspect of algebra will be most important. All of this will make much more sense when we are actually doing some, but I'm sure by now you know when you see particular things, you've already picked up, hopefully, that if you see terms with fractions, then you might be getting a common denominator. Just things like that. I'm sure they're things that will come to you as we see them in the examples. Basically, you're showing that the left-hand side is equal to the right-hand side, and your maths toolbox, all those things you've learnt throughout the year, become your very best friend. You need to know them inside out and access them as easily as opening a box and taking something out. Step 4, the very last step, I really should make a comment about that, in that if you have set out step 1, 2 and 3, as I've shown, step 4 requires nothing more than a statement, because it's logical to make this conclusion that the statement is true if you've, like I said, if you've followed this process. I think I will stop the video there and delve a little bit more into just type 1. So when I produce a video and I call it type 1, you will know it's only about a statement involving the sum of terms and so on. So that if I name these little videos according to the type of statement, then you can pick one very easily and revisit it if you're having trouble.